Hi everyone, we are Team Segmentation 4 and our team members are Changjun, Hayden and Josiah. This is our presentation for the 2023 RoboCup CoSpace Rescue Singapore Open U19 category. All of us are from Singapore, Anderson Secondary School, Secondary 3. All three of us have participated in the RCAP CoSpace Rescue Singapore and also the Tianjin Invitational this year.
So, the main objective of the preliminary challenge is to pick up objects, which allow us to gain points. Each object gives a different number of points and has a different size. The size of the object decreases as the points gained from an object increase, making it more difficult to pick up objects with a higher value. Depositing the objects is another objective. Each robot can only hold up to 6 objects. Depositing these objects will free up space for more objects and give points equal to the total value of the objects deposited. Obstacles and traps will be present around the map. Going into a trap results in the penalty of losing all currently loaded objects and the points gained from it. Going out of the border results in a 10-second frozen penalty. There are also double point zones, the blue zones, where all objects picked up there will have double points when both picked up and deposited. Some areas, which are the grey areas, will reduce the robot speed by 80% when in it. There are position info loss areas as well, the black outline parts which will set the simulator's position X and Y to 0 when stepped on. Last but not least is to have a strategy to maximize the number of points gained with all of these factors. Here is a quick summary of the preliminary round map. There are 3 deposit zones which are close to the trap, obstacle, and swamp. Red objects are mainly concentrated at the top left of the map, and cyan are mainly found on the top right side of the map. Black objects can be found in the area above the double point zone. Here is the overview of our presentation. First, we will be talking about picking up objects, navigating around the map, targeting specific parts of the map, and sharing about the PID control that we use for path following. At the end, we will include our gameplay and our conclusion.
Now, here is the optimal combination of objects. Before we dive into the combination, I would like to highlight that there are red, cyan and black objects found around the map. They are worth 10, 15 and 20 points respectively. Super objects that are worth 90 points are made by a set of red, cyan and black objects after being deposited. There's also a super plus object that's worth 180 points, which is made by 2 sets of objects, which are 2 red, 2 cyan and 2 black objects. Super objects coordinate will also be given, which will be super useful information for the robot to pathfind. Here's a graph showing the scores for each combination: R for red, C for cyan and B for black. Super objects will be picked up in this calculation. As seen, the one with one set and normal super object gain 450 more points than full black. The 2 sets and super plus object perform significantly better with 450 more than RCBBBB. So we aim to get RRCCBB and collect the super plus object. Next, the ordering of object the robot picked up should also be optimal to minimize time wasted. We tried to get as many pairs of RRCCBB combo as possible to create more super plus object for points. Additionally, we only deposit object when the robot is fully loaded with objects. This is all to minimize the time picking up and depositing redundant objects. In order to avoid obstacles and other for pathfinding and navigation, we took a screenshot of the map and simplified the map into simpler colors with Microsoft Paint such as red for walls, yellow for traps, and white for free spots. We then used OpenCV to make a 2D array of numbers for each different color, such as 1 for wall and 2 for a free spot. Here, you can see how the map is converted to a 2D array of numbers. This 2D array can be used for pathfinding, which will avoid going near obstacles. The color sensors are used for both trap and swamp avoidance. Coordinates are used to avoid borders and ultrasonic sensors are used to avoid obstacles, and the steric changes depending on how close the robot is to the object. To deal with the position info loss zone, whenever the position is not lost, we will use the position X and position Y provided by the simulator. But once the robot enters an info loss zone, we will use odometry to calculate the new position X and position Y based on wheel speeds and compass of the robot using the formula below.
Since coordinates are given for the super objects, and deposit zones can be figured out by moving the robot in the simulator, pathfinding can be used to find the shortest path between the robot and target, as well as the path to it with the help of the 2D array generated for obstacles. But the question is, what algorithm should we use? There are 4 that we thought of. Breadth first search with the time complexity of O of v plus e, A star with the time complexity of O of v plus e log v, and Dijkstra's algorithm with the time complexity of O of v plus e log v, and also Bellman-Ford with the time complexity of O of ve, where v is the number of vertices and e is the number of edges. After some thinking, we decided on A star as it uses a heuristic, which is the distance from the robot to the target. This will make it pathfind towards the target more efficiently, so it will be faster than the algorithms in most cases, even though it doesn't have the fastest time complexity. As seen in the figure, the A star search shoots towards the target and does not search any unnecessary spots to avoid time wasted, while still guaranteeing the shortest path. After finding the shortest path, we still need to go to the nodes of the path, so we use the A10 function, basically inverse tangent with modifications, to calculate the appropriate angle for the robot to face in order to go to the node. The robot will then turn towards that angle and then move forward once it has reached that angle, and then it will eventually reach the node after moving forward. Now we will touch on zoning. There are certain zones in the map where objects are more concentrated. Therefore, we can increase the efficiency of the robot's movement by getting it to search in these spots rather than some other less concentrated zones. PID control, which stands for proportional, integral, and derivative, is a useful control loop mechanism to fix errors. It can be used for smooth path following to fix errors, which will be the distance between our target angle and our current angle, in order to turn to an angle smoothly. This is the full formula for the PID control. E of t is the error value, which is defined to be any value that measures how far off we are away from our desired condition. In our case, the desired condition is the target angle, and the error is how far our current angle is away from the target angle. U of t is a control variable which measures how fast you want to move. In our case, it is the steering rate of the robot towards a target angle. U of t is calculated by the sum of the proportional, integral, and derivative gain, which I will talk about later. Kp is the proportional gain, which is a constant that is multiplied to the error to scale it properly. This gives us a linear relationship between the error and the steering rate, U of t. This makes path following smoother as the robot now knows to turn faster if the current angle is very far away from the target angle, or to turn slower once it's closer to avoid overshooting. Ki is the integral gain, which is another constant multiplied to the integral to scale it properly. The integral is from 0 to t of the error with respect to time. This is basically a fancy way of saying the accumulated sum of errors from the start till now. Steady state error occurs when the robot has a very small error, such that the proportional gain is not high enough and the robot ends up being stable but still having an error. Summing up the errors across a period of time allows the robot to realize that there still exists an error and to correct it. Kd is the derivative gain, which is a constant multiplied to the derivative to scale it properly. The derivative is the derivative of the error with respect to time, basically a fancy way of saying the rate of change in error. Overshooting still occurs frequently with proportional control. This helps with that, as it will reduce the steering rate if the rate of change in error is too fast, meaning that we are going too fast and need to slow down to avoid overshooting, and vice versa.
Here is a video of our robot run in the preliminaries. First, the robot will pick up the object using the RRBBCC combo. Then, it will pathfind to the deposit zone. In the last minute of the game, the robot will pick up the generated super objects and deposit them. I found this competition very interesting as we are able to apply the knowledge gained to the real world. An example of this would be concepts such as pathfinding, which can be applied to find the shortest path, for example, in Google Maps' shortest path algorithm, but implemented on robots. Additionally, extrapolating the robot's future position will also be useful, as the position will not be given in real life, and there will be cases when there is no signal. Increasing efficiency will also be useful to reduce the time taken to finish a specific task. Finally, avoiding obstacles can be used in car autopilot technology such as a Tesla car, which is very popular nowadays, as it can detect nearby obstacles and avoid them efficiently. In conclusion, the strategies we implemented drastically improved our score, from an average score of 300 without the strategies to an average score of 2000 and above with all the optimizations. Our main weaknesses are that the robot was inefficient in zoning around maps. Additionally, it also had a poor obstacle and swamp avoidance. In general, we were quite happy with our score. However, we also think that we could definitely have done better. In terms of further improvements, we think that we can improve the efficiency of the zoning around the map for objects. At the same time, we can also find a better solution for obstacle and swamp avoidance. Through this competition, we have learned about how A-star works, the heuristics for it, and that it guarantees the shortest path. We have also learned about how trigonometry can be applied to many things, despite seeming to have nothing to do with math. We have also learned about OpenCV application to process images and to generate 2D arrays from it. We have also learned how to efficiently debug as well, and last but not least, we have also learned about PID control, which is a useful optimization. We would like to show our gratitude to our seniors who have guided us throughout the competition. Additionally, we would also like to thank our teachers for allowing us to participate in this competition. Finally, we would also like to show our gratitude towards the organizers for organizing and managing the competition. Finally, we would like to sign off with a quote. No matter how much falls on us, we keep plowing ahead. That's the only way to keep the roads clear. By Mr. 𝗥𝗍𝗄𝗽 𝗦𝗶𝗴. This quote summarizes our experience pretty well, that we need to persist even when faced with a huge number of issues and a lack of time. Thank you for your attention.